Okay, so section 4.2, we were solving problems like this. X double prime plus 4x equals cosine t, where x is 0 equals 0, and that happens to equal x prime is 0. And do you remember what we did? We had a rule here. In fact, we had two rules. What was our rule for the Laplace transform of the derivative?
It's equal to the integral of 0 to infinity of the derivative times e to the negative st.
Which we integrated by parts, and we learned that that turned out to be s times the Laplace transform of x minus x at 0, which we wrote as s times capital X minus x at 0. And then we used that theorem again, and we came up for a rule for the Laplace transform of the second derivative. That had s squared capital X minus
S times capital x at 0 minus x prime 0.
That's correct. So the way this worked is the s's went down, so I started with s squared, s, and then the s's disappeared. Meanwhile, derivatives went up, so I started with x prime. Okay, so we're going to make those substitutions. For x double prime, I'm going to substitute this. So I have, this equation becomes s squared, x at s, minus, but this is kind of nice, what's s times x 0? 0. Minus x prime at 0. 0, those go away. Plus 4 times the Laplace transform of x equals the Laplace transform of cosine t. I go to my magic list of Laplace transforms. The Laplace transform of cosine t, s over s squared plus 1. S over s squared plus 1. All right. Now, generally what you want to do at this point is you want to get all the things that have capital X on the left-hand side of the equation and all the things that don't have capital X on the right hand. This one's really nice because that's already done for us. Why do I want all the things with capital X by themselves on the left-hand side? I can factor it out. So I factor out a capital X, and I'm left with, a s squared plus 4 equals s over s squared plus 1. Say that again.
Wouldn't be x s capital S minus 4 so s.
I can't hear you, Greg. You gotta speak up.
Where is your s for?
Where's this s? Right there. I just factored out. There's a capital X here and a capital X there.
Yeah.
So I factored it out. So there's my s squared. All right, so I get this capital X all by itself. Capital X is s over s squared plus 1 times s squared plus 4. Now, what I need to do to finish solving is, remember this capital X stands for Laplace transform. I really want little x, so I have to do the inverse Laplace transform. That's correct. The problem is, I look at my big list of transforms, I don't see any that have this form. I don't see any that have an s squared plus k and an s squared plus another k down on bottom being multiplied like that. So it's partial fraction decomposition. That's exactly right.
So it's A over S squared plus 1 plus B over S. Oh.
No.
Oh, it's the same numerator, right? So you could just break
We're going to have s squared plus 1 on bottom and s squared plus 4 on bottom. Those are quadratics which do not factor. When you have quadratics that do not factor, what do you need on top? Linears. That's correct. So this has to be as plus b, and this one has to be cs plus d. When you have quadratics on bottom which do not factor, that means you're going to have linears up on top. So we need to solve for 4 variables, which means we're going to end up with 4 equations with 4 unknowns, and that will lead us to 4 solutions. That's correct. It's all matrix. All right. I'm going to clear my fractions first. I'm going to take this partial fraction here, and I'm going to multiply everything by the common denominator. So I'm going to have s equals as plus b times s squared plus 4 plus cs plus d times s squared plus 1. Now, for those who took Calc 2 with me and remember doing these partial fractions, I had a little trick that I like to do. What I like to do usually is pick a number that I could plug in and get zeros into these things. And then it was easy to solve for the other letters. I can't do that? Sure I can. I'm going to pick my favorite letter. I'm going to let s equal I, the complex number. All right, so this is a George Hrober original trick. I've never seen this in any book where you plug in complex numbers. When I plug in complex numbers, why do I like s equals I? What does s equal I do right here? It makes that 0, which means this whole part is 0. So I have I equals AI plus B times, what's I squared? Negative 1 plus 4 is 3. So that's the same as 3AI plus 3B. So what has to happen now is the real numbers on the right-hand side have to equal the real numbers on the left-hand side. Negative 1 plus 4. So what are the real numbers on the right-hand side? 3b. So the real numbers on the right-hand side, that's 3b, have to equal the real numbers on the left-hand side. There aren't any real numbers on the left-hand side, so 3b has to equal 0, which means b is 0. And similarly, the complex numbers on the right-hand side, what are the complex numbers on the right-hand side? 3ai has to equal I. So A has to be 1/3. So this is the shortcut for solving 4 equations, 4 unknowns. I'm going to repeat, and I'm going to plug in my second favorite number. What's my second favorite number to plug in? 2i for this problem.
Is it always going to be I and 2I?
No. It's I and 2i because I makes s squared plus 1 equal to 0. And it's 2i because 2i makes s squared plus 4 equal to 0. I'm plugging in numbers that make half of the problem disappear. That's the trick. So I get 2i equals c times 2i plus d times, okay, now what's 2i squared? Negative 4. And negative 4 plus 1 is negative 3. So that's negative 6 ci minus 3d. And I do the exact same trick with equating the reals and the complexes. minus 3d has to be 0, which means d is 0. And similarly, minus 6ci has to equal 2i. So c is negative 1/3. So personally, I think that's an awful lot easier than setting up 4 equations with 4 unknowns and even using my calculator to solve. If you want to do it that way, you certainly can. Your choice. All right, so almost done now. Now we have capital X of S is, let's see, we ended up with A being 1/3, so that's 1/3 S over S squared plus 1, plus C was negative 1/3 S over S squared plus 4. Final answer. X of t is, I go back to my magic sheet of Laplace transforms. I'm looking for something that has S on top and S squared plus 1 on bottom. S on top and S squared plus 1 on bottom, that's cosine. So that's 1/3 cosine t minus 1/3 S on top, S squared plus 4 on bottom, cosine 2t. There's my answer. Questions on that?
Oh, boy.
Oh, no, we're not done yet. Only just begun. We got a good half an hour to go here. What I want you to notice is I think this is kind of an interesting process. How would we have done this back in chapter 2? We'd have found the r's, which means we would have solved the complementary equation. And the complementary equation would have had r squared plus 4.
So it's 4i.
So it's 4i, so we would have had a cosine 2t and a sine 2t. And then we would have had to find the particular solution, which would have had an a cosine t plus a b sine t. We'd then have to take the first derivative, take the second derivative, plug it in, figure out a and b. Then we'd have to combine our complementary solution and our particular solution, plug in our initial conditions, which would have again involved taking a derivative, plugging in numbers, and solving yet another system of equations. The Laplace transform method finds the complementary solution
Much faster.
and the particular solution at the same time. So I think that's kind of neat, the way it does it. It finds them both in one.
So if it's not a homogeneous equation, then it's actually easier to do it this way.
Okay, so if it's not a homogeneous equation, it's actually easier to do it this way. And I'm not sure it's easier.
Well, it takes less work, maybe.
Maybe a little less work. Once you get familiar with these Laplace transforms, maybe you would be convinced it's easier. But what we did before was really just a lot of algebra, plugging stuff in, solving systems of equations wasn't too bad. But again, remember the big thing we're building up to, we're still not there,
Graduation.
is graduation for some of you, yes. The big thing we're building up to in this course in particular with Laplace transforms is what happens when these coefficients are not constant. Then the stuff we learned in chapter 2 doesn't work. But what we're learning here in chapter 4 will work. You can use Laplace transforms to solve those. Okay, but anyway, I just thought I'd point that out. That I think that's pretty interesting that it finds both the complementary and the particular at the same time. One technique.
Sorry, are we getting the partial fraction decomposition?
Quite often, you're going to get to the point where you get this capital X, and in most of these problems, I would say yes, you're going to have to do partial fractions. Maybe not all of them, but probably most of them, yes.
Good teacher teaching partial fractions.
Good thing you learned partial fractions before, that's right. Other questions?
When you say find a number that makes I, well,
Okay, so let me show you the way it usually works when you don't have so many complex numbers, maybe. Let's say you had, here's a good one. Problem 20, maybe out of the homework. I like 22 better even. Number 22. 22 has, you want to find the inverse Laplace transform of 1 over s times s squared minus 9. It was supposed to be s squared minus 9, but I started writing a plus, so I wrote it as s squared plus negative 9. All right, so we're going to do this problem twice, and you can tell me which way is better. This is the inverse Laplace transform of 1 over s times s minus 3 times s plus 3. So that bottom factors. If that bottom factors, what does that tell you to do? Partial fractions. All right, so we're going to come down here. We're going to have 1 over s times s minus 3 times s plus 3. This one's easier in the sense that everything is linear. So our partial fraction decomposition is just a over s, b over s minus 3, and c over s plus 3, because all three terms are linear. We clear our fractions. We multiply by the common denominator. We get 1 equals a times s minus 3 s plus 3 plus b times s minus 3 plus c times, nope, that should be, I'm sorry, b times s plus 3, and then c times s minus 3. So if you read a typical calculus book, what they tell you to do is they tell you to FOIL this out, expand this, and then they do a process called equate coefficients, and you end up with 3 equations with 3 variables. That works, but that's the hard way. The easy way is pick your favorite number. 0 is one of your favorite numbers this time. Why do you like 0? Because when I plug 0 in, it gives me 0 here, and it gives me 0 there. It makes both b and c go away. I get 1 equals a times negative 9. So a is negative 1/9. Then I pick my next favorite number for this problem. 3. Why do you like 3 so much? Because 3 gives me a 0 right here, which means it's going to make a go away. 3 gives me a 0 right there, which means it's going to make c go away. So 1 equals, that's going to be 3, that's going to be 6. 6 times 3 is 18b. So b is 1/18. And finally, I plug in my third favorite number, negative 3, because negative 3 makes the a go away, makes the b go away. I get 1 equals negative 3 times negative 6, that's negative 18c. So c is 1 over 18. Negative. Yes, thank you. All right, so going back up here, we're going to have the inverse Laplace transform of a was 1/9, so negative 1/9 over s.
C should be positive. Negative 3 times negative 6.
Okay, you talked me into positive 18. Do negatives make a positive. All right, so inverse Laplace transform of negative 1/9 s plus 1 over 18 over s minus 3 plus 1 over 18 over s plus 3. Final answer, minus 1/9, because the inverse Laplace transform of 1 over s is 1, and then that s minus 3 one, its inverse Laplace transform is going to be e. So s minus a, I'm going to have e there. So that's going to be plus 1/18 e to the 3t, and plus 1/18 e to the minus 3t. Standard partial fractions problem. Questions on that?
It was better because last time with the eyes, we really had to have a lot of experience to see.
Yeah. Easier when you use real numbers. I agree. Okay, the other option for this problem is there is a theorem that we can use. And the theorem says the inverse Laplace transform of, I want to write it the way they have it written here in the book. F of s over s is the integral from 0 to t of f of tau d tau. So if you thought s's and 5s were confusing, how do you feel about t's and taus? All right, so I'm going to write this as the integral from 0 to t of f of x dx, so I don't confuse my t's and my taus. So here's what this is saying. To the same problem that we did just a minute ago. If you have a factor of a 1 over s, you have a choice. You can do partial fractions. Or you can get rid of 1 over s if you're willing to do an extra integration. So this becomes the integral from 0 to t of f of x, where f of x is the inverse Laplace transform of just this piece. So what's the inverse Laplace transform of s squared minus 9? 1 over s squared minus 9.
That would be
It's
It would be 1 over 9 sine of hyperbolic and cosine.
it's we have a number on top and s squared minus k squared, right? We have a number on top which is 1, s squared minus k squared. So that's hyperbolic. However, if I have a 9 down here on bottom, I need to have a 3 up there on top. So this is going to be 1/3 hyperbolic sine of 3x. So I'm going to have the integral from 0 to t of 1/3 hyperbolic sine of 3x dx. What's the integral of hyperbolic sine?
It's been a while. Is it like 1 over the square root?
What's the integral of sine? Negative cosine. What's the integral of hyperbolic sine? The hyperbolics are even nicer. There's no minus sign. So, but we got a 3 here, so we're going to have to divide by another 3. So that's going to be 1/9 hyperbolic cosine of 3x, evaluated at 0 and t. Final answer is 1/9 hyperbolic cosine of 3t minus 1/9 hyperbolic cosine of 0. Hyperbolic cosine of 0 is 1. So 1/9 times 1 is 1/9. Yeah.
And then you know that the definition of a hyperbolic cosine is with 2 e's, and that's what it is.
The definition of a hyperbolic cosine has an e to the power divided by 2. So that's where the 18 is coming from, and that's where you get the e to the power. So this answer really is the same as that answer.
Craziness.
Okay? So when you get to problems there in your book, problems 17 through 23, they want you to use this theorem. You can use this theorem if you want, or you can use partial fractions to find the inverse Laplace transforms. Either way will work. Questions on that?
So you just use this rule when you can factor out 1 over s.
Right, this rule works when you have a 1 over s. Yep. All right, the last thing in this section, I don't know if we're going to have time today. We'll see. Anybody know Kramer's rule? You're doing it in linear algebra. You're going to. You're going to get a sneak preview today then. Kramer's rule is a technique for solving systems of equations. So let's make up a system of equations here.
Could be a simple one, or does it have to be?
2x plus 3y equals 5. Does that sound pretty simple so far?
Yeah.
Right. Minus 4x plus y equals 3. Now, truthfully, solving this one by Kramer's rule is overkill. You really should solve this one by elimination or substitution, but you can solve it with Kramer's rule. And we're going to need Kramer's rule for what we're going to do in a minute. So the way Kramer's rule works is you set up 3 matrices. The first matrix is usually called D. And D is simply the coefficient matrix. So that's going to be 2, 3, -4, and 1. So that's the D matrix. The next matrix you set up is a matrix called D sub x. And what you're going to do for D sub x, you're going to take these numbers over here, these answers, 5 and 3, and you're going to plug them into the x column. So that's the first column. So you're going to have a 5 and a 3 here. And then the rest of that matrix will be exactly like it is for matrix D, which means a 3 and a 1. And then the final matrix we set up is called D sub y. Any guesses on what you do for D sub y? You take these numbers and you put them in the y spot. So we're going to have 5 and 3 on the right. What are you going to have on the left? The same as what you had back up in D, 2 and -4. Okay, here's the solution. X is the determinant of D sub x divided by the determinant of D, which is, I have a 2 by 2 matrix here. How do I find the determinant? I multiply this way, 5 times 1, which is 5, minus, I multiply the other way, 3 times 3 is 9. Divided by, then I do the exact same thing for the D matrix. 2 times 1 is 2, minus -4 times 3 is -12. That's -4 over 14. And I can find y exactly the same way. Y is the determinant of dy over the determinant of d. dy, I go 2 times 3 is 6, minus -4 times 5 is -20. over the determinant of D. The determinant of D is 14. I already figured that out. I don't need to do it again. So that's 26 over 14. Questions on that?
So when does this come into usefulness if you could solve that all with one matrix?
You're about to see. Where do we use this? I agree, you could have solved this with one matrix, use the augmented matrix method,
Or just algebra?
or just algebra. Yeah, like I said, Cramer's rule is overkill for solving this problem. But we'll need it here in just a minute. And what we need it for in just a minute here, what's that? No? This is number 12. X prime equals x plus 2y. Y prime equals x plus e to the negative t. And our initial conditions are x at 0 equals y at 0 equals 0. So what do we have? Something we've never seen before. We have a system of differential equations. More than one differential equation at the same time. Laplace transforms can also be used to solve systems of differential equations. That's what I'm going to do. I'm going to take the Laplace transform. What's the Laplace transform of x prime? It's S big X minus x at 0 equals, that's big S plus 2 big Y. The Laplace transform of Y is big Y. Do the same thing to the bottom equation. What's the Laplace transform of Y prime? S big Y of S minus Y at 0 equals big X plus, what's the Laplace transform of e to the negative t? Let's see. E to the negative t, that means a is the number -1. So it's 1 over s minus -1, that's 1 over s plus 1.
And since x is 0 and y is 0, both equal 0, we just get.
Those are both 0, so those both go away. I agree. Now what I'm going to do, very much like we did when we had one equation, I'm going to get all the things that have capital X and capital Y on one side, and all the things that don't on the other. In other words, I'm going to write this as S capital X minus capital X minus 2 capital Y equals 0. And the second equation I'm going to write as minus capital X plus S capital Y equals 1 over S plus 1. That first equation, I can factor out a capital X out of these first two terms. So I'm going to rewrite this one more time. This is S minus 1 times capital X minus 2 capital Y equals 0 minus capital X plus S capital Y equals 1 over S plus 1. what I really would like to be able to do now is I would really like to be able to say capital X of S is something and capital Y of S is something, and then how would I get my little x and my little y back? I would do my inverse Laplace transforms. So the question is, how do I take this system of equations and get the big X all by itself? I'm going to use Cramer's rule. My other option would be, for example, I could multiply this bottom equation by s minus 1. I could multiply everything by s minus 1 and then add, and my x's would cancel out. But that's usually considered very difficult. It's usually much easier to use Cramer's rule on these problems. All right, so we'll come back on Wednesday and we'll start this problem again from the beginning. We'll do it all over again, and then we'll see how we're going to use Cramer's rule to separate the x and the y, and then we'll find our inverse Laplace transforms, and we'll be all done that one.